Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ikmal bin Azman. My matrix number is DE20000069. Bismillahirrahmanirrahim. We are from Group 7 and our project title is Performance of Cache Memory using a ParaCache simulator. For our group, obviously, like we introduced just now, the leader is Nurul Syafiqah binti Ismadi. The second one is Muhammad Ikmal bin Azman, which is me, and the third one is Muhammad Nazmi bin Ramli. For the outline, cache is a sort of a memory that is exceptionally quick and serves as buffer between the RAM and the CPU. It stores frequently request data and instructions so that the CPU may access them rapidly when they need it. In this study, we pursue to prove the performance of cache memory by testing each of cache mapping technique that available in this study using a ParaCache simulator. There are three types of cache mapping, but for this study, we will use two most efficient mapping, which is set associative mapping and direct mapping. The limitation of the project is that the simulation that we use are only capable to test either hit rate or miss rate of the cache. For the introduction, there are four things that we will explain to you, which is cache memory, project details, method of replacement, and write policy that we use. For the first one, cache memory. Cache memory is a chip-based computer component that increases the efficiency with which data is retrieved from the computer memory. It acts as a temporary storage area from which the computer processor can retrieve the data quickly. The processor can access this cache faster than the computer's main memory source. Cache memory responds to CPU requests 100 to 1000 of the time faster than RAM in a matter of a nanoseconds. Next, the introduction of a project details. In this project, we will use ParaCache simulation to test the performance of a cache memory. The simulation will test the hit and miss ratio of a memory cache based on the two types of cache mapping that I said earlier, which is direct mapping and set associative mapping. Obviously, for the objective of the project is to measure the cache performance. So, the memory size, cache size, and the given instruction to the cache will be constant to make sure we can differentiate and compare the performance of between the direct mapping and the set associative mapping. The method of replacement in this project is a first come, first serve. First come, first serve is an operating system scheduling algorithm that automatically execute queue requests and process in the order in which they arrive. This method of replacement is the most basic and straightforward CPU scheduling algorithm, and that's the reason why we use first come first serve replacement algorithm, because it is straightforward and easy to understand. And the last part of introduction is the write policy use. Based on this diagram, we are used write back with the write allocate policy. The reason why we use write back policy is because it has a better performance because it is more sophisticated, complex, and most used in the CPUs nowadays. And the last reason we use write back policy with write allocate is because it will take advantage of a temporal proximity, and the data that has been written soon will be read faster in the CPU. So I will pass the next part, which is a demonstration, to the Syafiqah.
My name is Nurul Syafiqah binti Ismadi. My metric number is DE200003, and I will be presenting about the demonstration of simulation of direct map cache and two-way set associative cache. I am Nurul Syafiqah binti Ismadi, and the first demonstration will be about direct map cache. So the cache size is 16, the memory size is 256, and offset bits of 2. So this is the list of instruction that we will use. We had submit number 3, hex 3, and it will be converted into binary. So The index requested will be searched in cache as highlighted in yellow because for index 0, the binary is 0, 0. For 1, it's 0, 1. For 2, it's 1, 0. And for 3, it's 1, 1. Valid bit will be obtained and analyzed. The reason why the valid bit is 0 is because there hasn't been any memory data stored into the cache yet. So therefore, the cache miss is obtained and cache is updated with the new set. The requested tag will be at the cache tag. So, block 1 with offset 0 to 3 is transferred into the cache. The valid bit will be obtained and analyzed, and since the valid bit is 1, then we look into the tag. Since the requested tag and the cache tag are the same, which is 0000, therefore cache hit is obtained. The index requested will be searched in cache as yellow. It's 01, so it will be placed here. Since the valid is 1, they will look through the tag, but when they compare, apparently the tag are not in the same value, so therefore cache miss is obtained and the dataset will be updated with the new tag, which is 0001. Cache miss is obtained because the requested tag and the cache tag are not the same. As we can see, this is the final result of the cache table. And this is the statistics. The hit rate of 45% and miss rate of 55%. Based on the demonstrations we made of the direct map cache, we can simply observe that in direct mapping, memory block is assigned to a specific line in the cache. If the requested line has a memory previously stored in it, it will update the line with a new memory and discard the old memory. So the next type of mapping will be two-way set associative cache. We'll be using the same cache size, the same memory size, and offset bits, and also the same list of instructions. So as usual, the instruction has been converted from hex to binary and allocated to tag, index, and offset respectively. And index requested will be searched in cache as highlighted in yellow. What makes two-way set associative cache different from direct map cache is that two-way set associative cache has two tables, meanwhile direct map cache only has one table, and it is divided into two. And the valid bit will be obtained and analyzed at both tables. So since there are no data yet stored in both tables and the valid bit is 0, therefore both of these AND get is missed. Therefore, cache miss is obtained. So the new dataset will be updated at the first table. The dataset will be updated in order. First, it will goes into the first table, and the next one will go to the second table. Both results in cache miss. Index requested will be searched in cache as highlighted in yellow. Hit, when it compares, will result into hit because the valid bit here is 1, meanwhile the valid bit here is still 0. Therefore, the result is cache hit. But the dataset will not be changed or updated in the table. Instead, it will be fetched from the cache. Since when the requested tag is compared to the cache tag, and both results into miss and results into cache miss. It will be updated at the second table. It will only be updated in the table only if the result is in cache hit. Same like this now, data is fetched from the cache, results into cache miss. Therefore, block 7 with offset 0 to 3. Therefore, no additional operation required, but it will be updated with new data, which is block 5 with offset 0 to 3. As we can see, this is the final result of the cache table. And this is the statistics for the two-way associative cache. It has the same hit rate and miss rate as direct map cache. Based on the demonstration done for two-way set associative cache, we can explain that this mapping is basically an improved version of direct mapping that eliminates the disadvantages of direct mapping. The problem of possible thrashing in the direct mapping method is addressed by set associative. It accomplishes this by stating that rather than having only one line in the cache to which a block can map, we will group a few lines together to form a set.
Hi, my name is Muhammad Nazmi Biramli, DE1900204, and I will continue for the conclusion for the analysis. So, in the final analysis, we can differentiate and compare the two of this mapping method that we demonstrate in this project, which is direct map cache, and the other one is two-way set associative cache. We learned that in the direct map cache, each block in main memory can only move into one block in the cache. Collision between blocks attempting to occupy the cache are substantially less likely with full associative mapping. With direct mapping, two or more main memory blocks may have to fit into the same cache block, but with complete associative mapping, they may go into different cache blocks. So, however, more technology is required to identify which cache block to employ and to search the entire cache. We can see that in our demonstration of two-way of associative cache, it has two ways of storing data, as in it has two tables that could fill up the cache memory. The easiest way to minimize the miss rate is by increasing the cache block size. By following the principle of locality, the cache block size will help to improve the miss rate. There are two basic types of the principle of locality, which is temporal locality and spatial locality. In this case, the larger block size will help with spatial locality. However, the larger block size can increase the miss penalty, which will take a long time to process a miss. Thus, to improve performance, the cache needs a second level cache to be wise. This process will make cache go faster and keep pace with CPU. The most ideal solution is by let a first level cache to be fast enough to match the speed of CPU, while the second level cache will be large enough to reduce the penalty of going to the main memory. For recommendation, there is 3 that we have recommend, which is first is principle of locality, a processor's tendency to repeatedly access the same set of memory localities. Principle of locality, a processor's tendency to repeatedly access the same of memory locations over a short period of time. Second is temporal locality. If something is accessed once, it will almost certainly be accessed again soon. And the next one is spatial locality. If something is accessed, something nearby, it will probably be accessed.
So the first question of Q&A, the unique features of your CAO project. The unique features of our project is it improves the efficiency of data retrieval. It saves program instructions and data that are utilized repeatedly throughout program execution, as well as information that the CPU is expected to want next.
For the second question, which is what does current trend of the computer architecture is related with our project. So the current trend of the computer architecture is related to our project is obviously everyone to make sure that their own computer to be more faster, more smooth and more efficient. Specifically to those who do graphic design on PC, which is it's rely 100% on their computer. This project will help them or us to understand better how to increase the cache performance, or maybe how to understand about how the data goes to the cache and so on. That's all for me.
Okay, now I'll answer the Q&A question for the number 3, explain on how our project can support the sustainable development. So by doing this project, we indirectly help in sustainable development goals according to the United Nations. One of it is SDG number 9, which is industry innovation and infrastructure, where by doing this project we can learn, compare with the analysis and make a conclusion on what we carry out through this project. Not only that, with the result of this project we can also know which method is better to use in the needs of industry and global infrastructure. Furthermore, by doing this project, make us to think creatively by thinking of methods that are better than the result of the project that has been undertaken. That's all from us, Group 7. Thank you very much for watching.